thanks. Thanks a lot for having me speak here. It's an honor. So first, who am I? This is a bit about my background. Background in graph and order theory and algorithms. And since 2007, I've been working at Argonne, where I have been working on a particular application. And so I'll speak about that, but after I motivate that, the result will be a relatively simple and easy to state combinatorial problem. And so if I lose you at some point during that process, of course, feel free to ask questions. But it won't be a really big deal because pretty soon we'll see something that's pretty straightforward. So what is this application? I work on a compiler called OpenAD. It's a specialized kind of compiler. And it implements something that we call automatic differentiation. This is a specialized compiler for large codes to run on supercomputers or that type of thing. And we have a primary application. It's this MIT general circulation model. It's a climate model. So it's a little bit more complicated than fighting fires on graphs, but hopefully I can take you through this. So derivatives are used all over computational science and engineering. People need them. Two extremely important examples are derivative-based optimization, numerical simulations like this climate model I spoke about. You often need sensitivities. And in this context, we're usually given code for a function f, something we want to evaluate. It might have many inputs, many outputs. And what we want is code that can compute f and also some derivatives, some derivative objects related to f at the same time. So we'll evaluate f at an argument, and rather than just getting the outputs of f, we'll get the outputs of f and also some derivatives at the same time. So how do we get derivatives computationally? Here's a very high-level overview. I won't get too much into details. You might be familiar with divided differences. Here we evaluate the function multiple times, and in doing so, we perturb the inputs a tiny bit. So we can tell how the outputs change with respect to the inputs by perturbing it, and we get derivatives. The main thing I want to emphasize about this method is it essentially treats f as a black box. What were we given? We were given code for f. Right? We were given an implementation. And so to treat it as a black box like this, we're kind of discarding some information we were given. And it also involves this parameter h, a step size, that we need to tune. These derivatives are inexact. So that's troublesome. A lot of people might point to what we call symbolic differentiation as a possible alternative. There are problems there as well. Again, we're ignoring this code we're given for f. It's from someone, from some climate scientist, and we can at least hope that we were given an efficient implementation of f. But when we feed this to Mathematica or something, we'll just give it a big expression, right? Symbolic differentiation like this takes expressions, and it will give you an even bigger expression. And so we can think about this as it's essentially you give it a formula and you get a formula back. So there's a lot of blow up here. There is an alternative. We call it automatic or algorithmic differentiation. Here, I'm talking about applying this in a compiler setting. So here we're given code for f, and we put it through our compiler, OpenAD. This is what we develop at Argonne. And we get this resulting code for f and some derivative object. And then we subsequently pass it to a traditional compiler to get machine code. So people will give us Fortran, for example. People still use Fortran, and that's one of our main applications. And so this OpenAD will take Fortran code. It's open source. There's I think it's a BSD-style license, and you can download it. And try it if you like. So the key difference is that here we treat f as a circuit, right? We're given straight line code, say, and we treat it as a circuit, and we append to that additional gates, essentially, in order to evaluate f prime. So that's the key difference. There's a ton of overlap in evaluating a function and the derivatives. Symbolic differentiation, not only do you not get any of that overlap, really, you end up with a formula. You could hope subsequently that your compiler is smart enough to do something about that, but what people observe is that this simply isn't practical. It doesn't work in practice. OK, so here is the abstraction. If you want, you can ignore these labels in this graph for now. So here's how this works. We're given straight line code for f, as I said. And abstractly, we know that this straight line code can involve arbitrary unary or whatever operations. We can always make a graph from this. It's like going from a straight line code to an arithmetic circuit, or a circuit. And so when we do this, the variables are going to represent temporary values computed as the function is evaluated. And the differentiation part happens when we attach variables to these labels. So on the level of this code, for these individual operations corresponding to vertices, we do something kind of symbolic. Because we know that these are going to be operations executed by a computer on some level, and so we can trivially, on some level, we can differentiate these things by library lookup, say. And so all these vertices take real values when we evaluate the code, and so we will add code to evaluate the partial derivatives, which will also take real values when this code is evaluated. And what remains is to do what we call accumulation. And that means taking these local partial derivatives on these edges of each one of these individual functions that's being applied and combining them into overall derivatives. So from a theory perspective, you might be familiar with Bauer and Strawson's paper, where they use this kind of idea to prove lower bounds. So how I'll be talking about this, the type of thing I'll be proving is slightly different, but it's the same idea as what's in there. And so this is the problem I'll be addressing. This tells us that the derivative of any output of our function with respect to any input can be evaluated like this. We take the sum over all paths. So this represents the paths from some Si to some Tj, the sources and sinks, or terminals. Take the sum over all paths of the products along the path. Right? So we've associated every edge with an indeterminate. And for the purposes of this talk, this will be our input. We're given a DAG, directed acyclic graph, and we want to evaluate this function. So these are the individual entries of the Jacobian matrix. And if we want some other kind of, if we just want one partial derivative, we just consider the part of that graph that applies. OK. So are there any questions about, we can forget that we're actually doing derivatives, and it's simply a matter of we have a polynomial or a collection of polynomials, and we want to evaluate them. We're going to be evaluating them with circuits. Any questions? OK. There can be an exponential number of paths in a DAG, right? And so this function could have an exponential number of terms, but we can evaluate it easily by doing, one way to think of it is dynamic programming, right? OK, so there's an upper bound that we've had for decades. So that's OK. Next, I'd like to point out the fact that, OK, so I've said that we're given a straight line code. You say, OK, any real computer program is going to have loops and branches or whatever, right? So is this just a toy problem? Does this just only work for toy instances, small, insignificant instances? the answer is no, and it's because this might represent some function that's deeply nested inside a loop structure and might actually dominate the whole runtime of what's going on. And so when we want to optimize the evaluation of these derivatives, even a small gain in the number of operations performed might turn out to big savings overall if it's some numerical kernel that dominates the computation. OK. Here's an observation. What do we get? What is the matrix that we get if we evaluate everything in here? Well, it's actually the same as multiplying two matrices together. So look, from here to here, we take what are the paths? From there to there. The other path is from there to there. So this is nothing more than we're describing the way to multiply two matrices, right? So as was mentioned, has been mentioned in the seminar before, we don't know how to prove lower bounds on matrix multiplication. The best we know is n squared, right? So what can we hope? Here we see that our problem contains matrix multiplication as a special case, so what can we hope to say about the complexity? How can we hope to prove lower bounds? The key is we're restricting ourselves to a semi-ring. And that means restricting ourselves to monotone computations. Our circuits are going to be monotone. Now, in this world, we actually can prove things. Here's an example. Jerem and Sneer showed in 1982 that you can read this result as saying that you can't do better than the schoolbook method for matrix multiplication. That's essentially what this says. And it even, well, OK. Right. So the point is we can prove things in this world. And actually, I discovered this because Sasha pointed me towards a related paper maybe almost a year ago, and that was how it's kind of the genesis of a lot of what's in this talk. So I might come back to this. OK, so why am I restricting myself to a semi-ring? So this problem, as I've stated it to you, has been studied for decades in the context of automatic differentiation. And so, it was kind of, people have been studying it in this way for some time. And I'm not quite sure, but I imagine it's some combination of the following. When we restrict ourselves to multiplication and addition, we have nicer numerical stability properties, without going into it any further. It also seems more natural, at least in the sense that, we want to make statements about the structure of derivatives and computing derivatives. If we want to get into proving lower bounds on multiplying two matrices, that's someone shouldn't be us doing that. That's maybe someone else's job. And it's also maybe something more fundamental. It's the structure of the chain rule, and maybe this should also have some meaning and be interesting in semi-rings when we're restricted in this way. So OK. So now I can give you a proper outline. I'll begin with a formal definition of the computational model I'm going to be using. It's essentially monotone arithmetic circuits, if you're familiar with those. Then I'll present some results. All my results are concerning ST-DAGs. Those are graphs that have a single source and a single sink. And so what we're going to be computing is just a single monomial. That makes things a little bit easier to think about. And so I'll present some tight lower bounds for a number of special classes of graphs. And these are the first results of their kind, essentially. We don't know much about this problem theoretically at all. Then, depending on how much time I have, I'll get into some discussion. The main problem, ultimately, we're interested in is we're given a DAG, and we want, say, an algorithm to find the smallest circuit, right? Because we could get anything as we could get any code from somebody, could have the structure of any DAG, at least that's what we're assuming. So we want to know how to, is there such an algorithm? It's been assumed, again, for decades that it's NP hard, but there's no proof. OK, so I wasn't here when Amir spoke, but I saw the talk online, and there was people got into some discussion about the difference between computing a polynomial and a function. So you talk about different fields or semi-rings, and so I might have something to say. I have something to say about that. So hopefully there will be time for that. But for the meat of this, there will be no difference between computing over the semi-ring of real numbers and computing polynomials with these circuits. OK, so let's get started. Semi-rings, these are the semi-ring axioms we'll be working with. Both multiplication and addition are associative and commutative. Multiplication distributes over addition, and we have identities. 0 is a multiplicative annihilator. I like that term. OK, and the key, again, is that we have no additive inverses. So that's why we're restricting ourselves to monotone circuits. OK, so by a monotone arithmetic circuit, I mean we have indeterminates from our set X. And here's the key restriction. We only allow positive constants. So in regular arithmetic circuits, you simulate subtraction by allowing, you say, include -1, right? And then you can do subtraction. But we only allow positive constants. All our gates are in degree 2. The standard multiplication addition gates, no problem. It's going to be easy for us to think about these polynomials in terms of a set of sets representation. So polynomial is a set of monomials, and a monomial is a set of variables. OK. So here's an example. Here is a very small graph. Here's the thing we want to compute. And here's an example circuit computing it. We'll see this circuit again. OK, so what can we say? Our polynomial is multilinear, right? It's linear in each of the variables. So I want to impress on you that monotone multilinear circuits have some very nice properties. And so we'll be using those properties in our proofs. Nissan and Vidgerson observed this, and they also had a paper in 1995 that also used partial derivatives in proving lower bounds. Again, what I'm talking about is not quite the same thing, but they also kind of initiated a study of multilinear circuits. Here's another way of looking at the previous statement. Monotone multilinear circuits are multiplicatively disjoint. So the important part of monotone circuits, I guess, is that once we compute something, we can't get rid of it again. So the whole circuit has to be multilinear. If we ever multiply a variable with itself, we can never get rid of it again. And so we have this restriction that with respect to every product gate, the sets of variables below the two children are completely disjoint. That's nice. OK. This is basically the only piece of machinery that we'll need for our proofs. This notion was introduced by Jerem and Sneer in the paper I cited before. They called them parse trees. I guess they specifically mentioned it. They were inspired by parsing grammars and that type of thing. Lots of connections. And interestingly, there's actually a linguist here at the university who he had a book on semi-rings that I wanted. And I used this mechanism that they have in Eckhart, right, where I can ask them to get in touch with me if they like. And so I struck up a conversation with this guy. He does related things. He also works on semi-rings. He couldn't be here today, but I thought that was very interesting. OK. So basically, parse trees are going to chart for us where all the different monomials come from. So it include the root. For every sum gate, include just exactly one of the two children. And for every product gate, include both of them. OK, pretty straightforward, I guess. So it'll be easier to see here. Okay, this is the circuit we saw before. Here are the parse trees. Okay, so this one corresponds to that monomial x2, x5. Here we have another one, right, for the middle monomial. This one actually corresponds to two parse trees. And so we can think of it as the monomials partition the parse trees, and the value of monomial is the sum over all the corresponding parse trees. Here's our last parse tree. Right, okay. Great. So now we're ready to, now that we know what parse trees are, we're ready to move on and actually prove something, hopefully. Okay. So here are the three different classes of stdags that I'm going to address here in this part. By three homogeneous, I mean all the paths are length 3. So you call it that because the resulting thing we want to compute is a homogeneous polynomial, 3 homogeneous. The other one is complete stdags. So this is the single source, this is a single sink, and all possible edges between the vertices in the middle. You can think of it as taking a clique and take a transitive orientation. Okay. Series parallel stdags. If you're not familiar with these, I'll get to a definition soon. Okay, so first, these 3 homogeneous stdags. And as I mentioned, yeah, please.
So the theorem was that you can compute this polynomial over these?
The theorem is, if I'm given a DAG, if it belongs to any one of these classes, then I can produce an optimal circuit in polynomial time.
Oh,
Yeah. Yeah, yeah. So a circuit meeting the lower bound. Okay. So we saw correspondence with multiplying matrices before. In fact, any homogeneous DAG will correspond to some iterated product of sparse matrices, right? So here we see that we have a dense vector, possibly sparse matrix x2, and then another dense vector. That's what's going on here. And so here's what we can say about this. The number of multiplications necessary to evaluate what we want is the number of non-zero entries in this middle matrix, which may or may not be sparse, plus the vertex cover number of the associated bipartite graph that we get from just pulling at the middle. It's the, thinking of this as a matrix is the bipartite adjacency matrix of this graph. Okay. I think it's easier to show the upper bound first. Maybe you get some intuition of what's going on here. Basically, there's really only one thing we can do, and that is when we have a collection of these paths, so the paths are in one-to-one correspondence with the edges in the middle here, and we want to compute all these paths, what can we do? We can kind of pull out one of these indeterminates and distribute it over the others. So distributivity here takes the form of disjoint paths all sharing some other edge that goes along those paths. So what I'll do here is say we have a vertex cover H of this graph. And so without loss of generality, I'll assume it includes this vertex. What we'll do is the following. Just pull this part out. So we'll take care of computing all these paths by doing a multiplication, a multiplication, a multiplication, adding them all up. That's what all these additions are. And then we're going to take the whole thing and multiply it by this indeterminate. Once we're done, we've already taken care of all the paths corresponding to these edges in the middle here, and so we can get rid of them, right? And we also get rid of this edge and this vertex, and then just proceed again. Pick a next cover vertex, no problem. So here's an example of, so you can ignore these labels for now. That I'll explain those in the next slide. Here's an example of vertex cover and the corresponding circuit we would get. Okay, so here's the lower bound. Remind you that there's a one-to-one correspondence between the monomials and elements of this middle matrix, right? This x2, and that's what these inputs represent. They come from that set. So we observe that basically there's three different types of parse trees we can have for any given monomial. The important part is, so here I've shown the important product gates from them, and they're important in the following sense. They're kind of the place in this parse tree where indeterminates come together. So there might be constants in there somewhere, but we ignore those. And so every parse tree is going to have a place where first we have two variables coming together, and then an upper one where three variables come together. So I'm going to partition I'm only going to consider these important kind of product gates, and I'm going to partition them into the lower ones and the upper ones. The lower ones are where the two of them meet, and the upper ones are at the top here, where the third one comes in. And so, right, there's only three ways we can do this. So, show that if we have a parse tree of this type, I call it type 3 on the previous slide, we can, without loss of generality, we can always turn it into one like this. Why? Well, if we look at this lower product gate, right, once we've included an indeterminate from x1 and also an indeterminate from x3, we're fixed. This can only apply to one monomial. We really can't do anything else with this at all. So that would mean multiplying, say, this edge and this edge, we can't do anything else. So what we'll do is remove this parse tree, and we're going to compute that monomial a different way. So when we remove at least two product gates, and we're going to add this, adding two product gates. So we don't change the size of the circuit. It might get smaller even. And this is just going to be of what I called type 1 on the previous slide. OK, so now to complete the proof, first observation, these lower gates, there's at least the number of non-zero entries in x2. There's at least that many of them. Why? Every lower gate, right, so now none of the parse trees look like this. Every lower gate has an element of x2 as a descendant. That means they all have to be disjoint. They're all pairwise disjoint. Because no element from x2 occurs in more than one monomial. So those all have to be disjoint. And from there, especially now that we've seen the upper bound already, it's not hard to imagine how we could get a vertex cover from the upper gates. If this is our upper gate, we simply include the corresponding vertex. So if it's type 1, right, then we're going to include a vertex from this set. So that's the lower bound. Are there any questions about that? OK. OK. So the rest of the bounds are going to be proved in the following way. We're going to define some reduction rules. You can think of these as local transformations in the graph that turn G into G prime. And we're going to prove something relating the complexity of G to G prime. So we'll see that in some cases, particularly the classes of DAGs that I mentioned to you, we'll see that we can find a sequence with not too many operations, in fact, never more than the number of arcs in G, and we're going to reduce it to a single edge. So in this sense, in doing so, we'll build an optimal circuit for the graph. So here's the first one. This is something that seems intuitively obvious, and people have been assuming for a long time. But the question is how to prove it. Maybe it's not that difficult, but it's not immediately straightforward either. So I haven't mentioned whether or not the DAGs we consider have parallel arcs. The reason for that is, as you might suspect, we can ignore them, right? So by ignore them, I mean that we can simply add them and replace them with a single edge and go on from there. The question is, how can we prove that this is true? Works in the following way. We're going to, so this represents what happens in G prime. So if we assume that we have any circuit that computes for G prime, then all we have to do is add one addition gate, simply replace this x prime with x1 plus x2, and all of a sudden we have a circuit for our original graph G. Great. So how do we go the other way? Set x1 equal to 0. What do we have? We essentially have a circuit for G prime, if we just think of x2 as x prime. And in doing so, we remove at least one sum gate. Why is that? Well, if x1 has a sum gate as a parent, now we're doing something plus 0. Right, we can get rid of that sum gate, no problem. Well, the alternative is that all of x1's parents in the circuit are product gates. Well, that's no problem either, because those immediately become 0, and then we keep going until we reach some sum gate, which we can get rid of. So no matter what, when we set x1 to 0, we're going to remove at least one sum gate. And so this follows. And for the rest of the reduction rules, we're going to need a pretty straightforward lemma. Works like this. Consider any arc from some u to v. If there's no alternative path from u to v in G, then every parent of the corresponding input in the circuit is going to be a product gate. How do we see this? I think a picture is helpful. So there's u and there's v. Here's our circuit with x, u, v at the bottom. So if x, u, v has some sum gate as a parent, we'll just say the other child is beta. If this is the case, then for every parse tree that chooses x sub u, v here, there will be a corresponding parse tree that chooses some monomial from beta instead. This parse tree will correspond to some monomial when we finally get to the top. Say it's some monomial, whatever. It's right, blah, 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 blah. X sub u, v, blah, 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 blah. And there will be a corresponding monomial that has beta instead. This is only possible if there's some alternative path in this graph from u to v. Okay. Okay, so now we can prove our second reduction rule. Here we're looking at vertices that have exactly one in edge and exactly one out edge. We want to replace them with a single edge. This, again, is something that people have been assuming for a long time, but it's nice to prove it. Right, so it's very similar. If we have a circuit for G prime, all we have to do is add one multiplication, and we have a circuit for G. Right, we just replace x prime with x1 times x2, no problem. Now we have to show that we want to set x1 to 1 this time, not 0. Because the result will be, again, we want to be able to remove something and obtain a valid circuit for G prime. So now we have to set this to 1, and that's why we need our lemma to prove that when we set this to 1, we remove at least one product gate. right? So that's how we use the lemma. We know that every parent in the circuit of x1 is a product gate. That's, we need that in order to guarantee that when we set this to 1, at least one product gate is removed. Okay, so here is a definition of series parallel graphs. You might already be familiar with this. If not, you still might see where this is going. So the series parallel graphs are exactly those graphs that when we apply the two reduction rules I've mentioned, they can be reduced to a single edge. This is interesting, though. We also have that these are exactly those graphs where there's a circuit for what we want to compute that is also tree structured, or structured like a formula. I don't have a good sense of how obvious that is, but I think it's at least interesting.
Why like the formula? Why not just the formula?
Because it is a circuit that is also a formula, right? I'm also not duplicating any of the inputs, right? Okay. There's one final reduction rule. This one is kind of a hybrid of the other two, but it'll be used in a very different way. So the conditions now are that V has exactly one in edge. That's like the series rule we saw before. And again, we have this restriction of there's no alternative path from V to W, because what we're going to be doing is getting rid of x2. So intuitively, what's going on here is that for every path that uses x3, there's a corresponding path that uses x2, right? Why? V has only one in edge, so every time we take x2, we must have taken x1 immediately before. That means we started there. So like the case with parallel edges, we again have this one-to-one correspondence between the paths. Here's how these are related. Two operations, one multiplication and one addition. Why? Because in order to given a circuit for G prime, we just have to replace x prime with x3 plus x1 times x2. Going the other way, now we're setting x2 to 0, and we want to show that we remove at least one product gate and at least one sum gate. So like before, since now we're setting it to 0, all right, so we have that all the parents of x2 in the circuit must be product gates. So that's straightforward. So we definitely remove at least one product gate. And again, as we set something to 0, we'll keep going up, eating product gates until we hit a sum gate. And that sum gate will also be removed. And so it follows that we need to show that there's at least one sum gate in the circuit. There will be, because there's definitely more than one path, right? So that's this last reduction rule. Now how can we use this to reduce a complete ST-DAG to a single edge? So here's a complete ST-DAG on 6 vertices. I've drawn it in a very particular way. All the arcs involving the source and the terminal sink are drawn up at the top, and all the edges between these intermediate vertices are drawn below. Why? And what we'll do is we'll successively remove every single one of these edges that occur between intermediate vertices. So we will be able to continuously apply this rule, removing each one of those edges one by one. When we're done, we'll actually end up with this. This is a series parallel graph. We use the other reduction rules, and now we have an optimal circuit. Okay, so to summarize, using these reduction rules, these are what we might call optimality preserving reduction rules. What does that mean? It means that no matter what, no matter what graph we have, when we apply them, we know we aren't kind of leading down the wrong track. So all these reduction rules should be included as like a pre-processing step. If we don't know how to solve this problem in the general case, there are tons of heuristics, and so why apply any heuristic before we've done all these reduction rules that we can, right? Here's another observation. We saw that homogeneous DAGs have this correspondence with iterated matrix multiplication. Well, now, with this series rule, with this rule of the rule of two edges in succession, think about it the other way. Now we're kind of placing a vertex in the middle of an edge. We're subdividing the edge, right? So we can use this to turn any DAG into a homogeneous DAG. Just keep applying these. Place every vertex on the lowest possible level, and any edge that goes between two different levels, subdivide it. Keep applying this. We've got a homogeneous DAG, and we know exactly how we've affected the complexity because these reduction rules go both ways. So let's say we had an algorithm that could solve this for all homogeneous DAGs. Well, I claim that that is an algorithm for all cases. Why? Take any graph, subdivide these edges, homogenize it, run your algorithm, and then we can go backwards. We know exactly how the complexities of these two graphs are related. And so in particular, it actually takes a bit more machinery, but you need to show that in this graph, when we multiply x1 and x2, that's basically all we're doing. So up to isomorphism, you can show that if we kind of add a dummy variable, it might be tough to deal with, but with a little bit of finagling, we can get it to work, and it's no problem. Is there a question? Okay. All right, so this all happens in polynomial time. That's important, and that's great. The other question is, I guess this type of approach comes up in parameterized complexity, where maybe we can make some statement like, any graph that we can't apply a reduction rule to can only be so big, or something like that. So that's a possibility, another possibility. So I think I have a bit of time for some discussion. So what have we seen so far? Right, I just mentioned this correspondence. The first bound was for these three homogeneous ST DAGs. And we saw those basically exactly the same as bipartite vertex cover. So we don't know, for this general problem of given a DAG, find a circuit, we don't know the complexity. But if we came up with a linear time algorithm, that would be a big deal, because this goes both ways, essentially. So at least we know there's no linear time algorithm, or probably isn't. And we saw these reduction rules. So is there progress towards this original problem, this problem of the optimization? Well, at least now we can prove some lower bounds, because we didn't know that before. And also, I'm personally starting to suspect that maybe this problem is tractable. But who knows? It's definitely one of those ones that you have to, I guess on Monday, Wednesday, Friday, you have to try to prove it's hard, and on Tuesday, Thursday, you have to try to find it out. OK. Here's what we do know about the complexity, though. Let's say we change the problem specification so that, all right, before, every edge had its own variable, and there was no relationship between the variables. No variable could occur on two different edges. But if we just relax what's going on just a tiny bit, and we just say that some edges have the multiplicative unit, have 1 on them, already the problem becomes hard, and even for very simple cases. So here's the corresponding. So this is, we would have thought of this as a regular 3 homogeneous ST DAG before, but now all these edges in here are unit edges. And we have this result from Gonzalez and Jaja that evaluating this is NP-hard. This is a bilinear form where this matrix is a 0, 1 matrix in the middle. What's actually going on here is it's a biclete cover, so we need to cover the edges. Oh, I'm sorry, it's not cover, it's a partition. We don't want to compute something more than once. We want to partition into bicletes. The way it's different is to give you a handle on why these unit edges change the problem. Let's say, it's kind of complicated. Let's say that we do have a four-clique, 2 vertices on this side, 2 on this side. Well, we can get all those paths by, let's say it was, it's not, but let's say it was these 2 and those 2. We could add these 2 values and add those 2 values, and with a single multiplication, we could address all 4 of those paths. So it changes a lot when we allow these unit edges.
How does compare multi-time distribution complexity? It's very similar.
I don't know how it, I don't know. Okay. So what happens if we interpret this function under some different semi-rings? We get some very interesting and familiar-looking functions, right? So let's think again. So what do we start with? What is this polynomial, this function we're computing? We're computing the sum over all paths of the product along the path. Well, if we replace our addition with min and our multiplication with plus, all of a sudden we're computing shortest paths. Now, if we take the variables and the edge labels and interpret them as 0, 1, maybe indicating that an edge is present or not, we get counting the number of ST paths. That seems pretty, this one's easy to see because the paths are the monomials. And now, all of a sudden, if every variable is a 1, then that we'll just get a 1, and we'll do sum over all counts the paths. So what's the key difference, at least in the bottom here? Well, it's this property we call idempotence. So it can hold for either operation. So here, it's the plus operation is idempotent, right? Because it's min now. And over here, it's the multiplication operation is idempotent because the variables take 0, 1 values. So everything we've seen so far, the optimal circuits don't have any constants as inputs. In our model of arithmetic circuits, we allow them, but it seems that you can't use them in this context. Why? Well, here's one really straightforward use of constants. Here, we might want a constant term, and that lets us calculate this polynomial with just a single multiplication, which I suppose you wouldn't be able to do otherwise. But this doesn't hold for homogeneous polynomials, right? So let's just say we're restricting just to homogeneous. Then if we're computing homogeneous polynomials in a monotone setting, everything we compute has to also be homogeneous. And so we'll never have any constant term. This also holds for path polynomials, polynomials that come from paths in DAGs, like in our problem. Why? Well, we can show that the parent of every constant input is a product gate. How do we show this? It's very similar to why when we said that if there's no alternative path corresponding to an arc, then it can't have a sum gate as a parent. Because some parse tree would choose that constant instead of some non-constant thing. And we can't have any, no path is a proper subset of another path. So constants in our context, so for homogeneous polynomials, constants can't be used in this way. And in our context, they can't be used in this way. The other way we saw that constants could possibly be used is that If we have a monomial that has more than one parse tree, then we might have some coefficients, and then they'll have to all sum up to 1. Why is it useful to have constant-free circuits? Well, everything's a lot cleaner, and in particular, you have the property that monomials and parse trees are in one-to-one correspondence. Because now the coefficient of everything is no less than 1, it can be exactly 1. Oh, and I should say, of course, I'm talking about monic polynomials here, where the monomials don't have coefficients. Because if you have some coefficient, you need it. You can't do anything about it, right? So in that context, it would be a meaningless question. So in the last 72 hours or so, I think I pieced together a way to show that constants can't be used in this context. So maybe I'll try it on you, and this will be the last thing. OK. So we'll talk about these two different semi-rings. This M is just the very same min plus semi-ring that I mentioned before. And this is the real numbers we've been dealing with this whole time. And in their paper, so Jerem and Sneer, they have a bunch of results that they want to apply to whole collections of semi-rings. And so what do? They essentially say that for certain kinds of computations, what's the difference between these two things? It's the plus operation is idempotent. And so this result shows that doesn't help you at all. So again, we're in the monotone world, but still very interesting, I think. So how does this help us show that constants can't help? So P is monic and multilinear. If it's homogeneous or it comes from some DAG, then constants can't help us. Why? OK. Say we do have a constant, or a circuit. Say an optimal circuit uses constants. Set all the constants to 1. So now, at least in terms of, with respect to the set of sets representation of polynomials I was talking about, that doesn't change at all. Because in terms of sets, everything's exactly the same. All that's different is now we might have had something like this in here, and now A is 1, and this other coefficient is also 1. And so now when we add this together, we get 2x2. Our polynomial is monic. We can't use 2x2. That would be problematic in the world of real numbers. But we can use this result and say, well, if we could do that, if we could get a smaller circuit by setting all the constants to 1, then we would also get, that would also be true in the case of this min plus semi-ring. But the min plus semi-ring doesn't have this issue, because when we take x2 plus x2, we'll get x2. So that contradicts this result. OK. So I'll write it up, and hopefully maybe it'll work. That'd be great. I'll skip this just to talk now about commutativity. Something else to observe, we didn't use commutativity in any of our results. And in fact, for 3 homogeneous ST DAGs, what we did is we said, let's say you do use commutativity, which is multiplying these 2 edge labels that aren't contiguous, right, non-contiguous region. If you did do that, it couldn't help you at all in that specific case. And in fact, it's been conjectured by Grievank and Naumann, some AD researchers. And their conjecture actually states that for a particular, we have these frameworks for applying heuristics. And so their actual conjecture says that there's always an optimal circuit that can be obtained within this particular heuristic framework. So all the heuristic frameworks don't use commutativity, and so their conjecture implies this. I suspect that it's true. And And so now we can look at this bottom part here and say now we restrict ourselves. Rather than looking at adding additional algebraic properties, we're now restricting ourselves. And so in order to remove commutativity, you can just say, OK, now we're just doing everything over 2 by 2 matrices. And I don't know the details of it, but so Grivank is the guy that wrote the book on AD. And he mentions that might be a possibility in some cases, where we might have matrices labeling the edges. So I don't know much about that, but it's at least a good way to represent what would be going on in the semiring. This is also related to semirings involving strings. I don't know too much about this either. But I guess the point is, if these were to collapse to each other, which this conjecture implies, at least for certain kinds of polynomials, then it would collapse this in with it and would apply to problems like that. OK. Here I want to acknowledge some people who I've had discussions with about some of these problems. These are my coworkers at Argonne. Uwe Naumann is now at Aachen. He was at Argonne. He's someone who studied this problem along the same lines as I have, but he has a different background. Andreas Grivank is arguably the main AD researcher. I've had very valuable discussions with people here at Chicago. And also Andrew Cohn, my roommate, helped me in preparing this talk.
So you have these optimal bounds for these special classes. Can you get any sort of like bounds that are not optimal for more general?
Yeah, excellent question. Yeah. I actually think there's a folklore almost result that that for ST DAGs, I don't know, that'll be fun. Okay, there's some people say that for ST DAGs in particular, the way of doing dynamic programming that I mentioned before will never do worse than twice the minimum. So I haven't seen an actual proof of that, but people mention that, and that reminds me I need to look into that more. But so for ST DAGs, and then so we have like a factor of 2, say. And that's actually exactly what we see with the series parallel graphs. If you try to do it, kind of evaluate it forward the whole way. By that I mean this dynamic programming approach, you essentially fix the associativity to be either all the way left to right or all the way right to left, my left to right to left. And you fix the associativity that way, and you take advantage of all the distributivity possible in that context. And so actually I think that series parallel graphs are the ones that exhibit the biggest gap between the best and what this dynamic programming approach does.
Can you show that these graphs occur for common computations that I want to do? Like, can you show, like, if I do a 5-point stencil, I'm always going to get this kind of graph?
I would love to be able to. I think the problem is that I don't know enough about these applications. We keep saying we'll talk about it and do that, but we don't. Right.